Okay.
Is that a new camera? Like you have to like.
Yeah, you have to baby it. Yeah, you have to, come on, you can do it. Okay.
Voice commands.
Yeah. All right, so today we're going to talk about implicit differentiation.
That just sounds insane.
I know, it sounds more impressive than it is. All right, so we need to back up. We need to talk about what implicit means. Careful, when you say something's implicit, it usually means it's sort of implied. It's not directly stated. All right, so we have that in math. We have explicitly defined functions. Explicitly defined means something like y equals log base 3 of x plus 10. I put in x, I know exactly what y is, right? I could also write that as y equals f of x equals log base 3 of x plus 10. So I can use f of x notation. That's also an explicit definition. I put in x, I just plug it in, and I get y. Here's one. No, sorry. C equals 10t plus 1,000. In the business applications we've been doing, what has C represented? Cost. And so, and actually, I'm sorry, change that to an x. So we've been defining cost based on the number of items. Do we usually just say C, or how do we usually write this? C of x. That's how we usually write it. Okay. Same thing with Q. Yes, 1,000 e to the 2t. This might be the growth of some sort of bacteria, right? Again, how do we normally write Q? Do we just write Q? No, we usually write Q of t. So when we're explicitly defining things, we're saying one quantity is exactly based on the other quantity. So I plug in the one, I get the other. And we use this f of x, c of x, q of t, that kind of notation. All right, so let's look at implicitly defined functions. You guys have seen these already. You just don't realize it. So here's one. You've seen that before, like when you solve systems of equations, right? We always put it in what we call standard form. It's not y equals mx plus b form. It's not point slope. It's not slope intercept. It's standard form. This is technically implicitly defined because it's not solved for y. So some implicitly defined functions I could turn around and solve for y, and they become explicit, but this is currently implicit. Let me give you another one. Again, not solved for y, so technically implicit. Could I solve this one for y? Yeah, sure. I can get y by itself, no problem. All right, what about this one? There's no way to... I can't solve this except numerically, which means to... Right. This is one that you would actually use graphical methods for solving. You cannot solve this one for y. There is no way to combine these in any way. So these are implicitly defined functions that you can rewrite, solve for y, but this one you can't. So the question is, I could rewrite this, y equals something, and find the derivative. I could rewrite this, y equals something, find the derivative. I can't rewrite this one. Does that mean no derivative exists?
No.
No, derivative exists. I have to find another way. That's today. So let's look at derivative notation. We need to make, I've been saying it, but I'm going to really emphasize it now. Okay, so if we say, if we're given y as some function of x, okay, just so that we know that x is the other variable we're working with. If I say y prime, right, what I really know that I'm saying, another way to write that is I say I'm taking the derivative. What do I say? The derivative with respect to x, really important, of y. Does everyone agree that's what I did? And then the other way I write that then is dy dx. So here I'm doing the derivative with respect to x. But if I do that for y, well, it's not 1, right? I mean, derivative d dx of x would be 1, but d dx of y, I write dy dx because I have to, because it's a function. I don't know what else to write. So similarly, if we were looking at c of t, I could say c prime is going to be d dt of c. Or I could rewrite that as dc dt. Yeah? And then we've just gone over the chain rule. That was another thing I was going to review, but we've already just gone over that, so we remember about the chain rule. So now let's look at some examples. So we're going to kind of work through this slowly, and then there's really, so we're going to talk about implicit differentiation, which is how we find the derivative for something like this without being able to solve for y. And then the only applications we're really going to do is our tangent line application. So that's what we'll spend the rest of the class on. All right, so first let's look at how chain rule connects to this. Okay, so d dx of, well, I wrote this, so I'll try and keep to it. 3x plus 3y. Okay, so let's remember what that says. Take the derivative with respect to x of x plus 3y. So I'm going to split that apart. And we're going to look at taking the derivative with respect to x, just of the x part, right? We can do that. And then I'm really just going to I'm just going to split off that derivative and do the derivative of the 3y part. So I'm just doing the derivative term by term. We've been doing that all semester. Well, our last 2 weeks anyway. Okay, what's the derivative with respect to x of x? 1, right? We know how to do that. That's just 1. That's easy. What's the derivative with respect to x of y?
Can we do that?
Yes and no. No, but it's dy dx, right? When we say derivative of y, we write dy dx. That's what we write. So here, this will just be 3 times dy dx. The derivative of x with respect to x, the variables match. So that's an important piece. Those variables match, so I just do a regular derivative. Do these variables match? No. So 3 is multiplied, so that carries through like always. But the derivative of y with respect to x, I just write dy dx. That's what that is. I don't know what else to write. Yes?
So I get that the variables don't match, but in the context of the equation, wouldn't the problem just be wrong? I mean, you're saying d over dx is the derivative of x. There's no x variable in the.
Let me hang on to that question, because when we get to an actual equation, I'm just kind of doing pieces right now. So if you hang on to that question for about 10 minutes, I think I'll answer it in a context that makes sense.
Roger, it was just
okay.
confusing.
Yes.
It
Yeah.
would just be wrong.
Well, hang tight, and we're going to get there. Okay, so let's look at this one. Let's do another one. So let's do. So here's a different example. d dx. This one's not in the notes, so I'm making it up. X cubed plus minus 5y. Okay, derivative with respect to x of x cubed. Can I do that one?
Yes.
Yeah, that's a basic, so 3x squared. Minus 5, so subtracting, multiplying by constant carries through. Derivative of y with respect to x. Derivative of y with respect to x. The words tell you it's a dy dx. That's, if I were to, I say, when I read this, I say it's the derivative of y with respect to x. That's a mouthful, but that's what that means. So if I try and say that, then I need to write it. All right, so let's try this other one. Let's try. I put the dot in there. I didn't have to, right? If there's nothing there, we know it is multiplying. So this is the derivative with respect to x of x times y. I said times. What do I have to do? Product rule. Yeah. So first and second. Hang tight. I know. Hang tight. First and second. So first times derivative of the second times derivative of the first.
No, I mean, you're good so long as there's an x in the equation. Like,
Just hang tight. I'll do another one just for you. Okay. So the first is x. What's the derivative of the second with respect to x? dy dx. Okay, that's what that means. Plus the second, which is y. What's the derivative of the first with respect to x? 1. Okay, I know this is weird having y's and x's. Cats and dogs living together. Anybody get that reference? Please tell me somebody gets that reference.
Ghostbusters.
Ghostbusters, thank you. Okay. Sometimes my movie references fall so flat. I did a Star Wars reference one time and somebody said, what? I'm like, really? These are not the droids you're looking for? You can't. Oh, pained me. Okay, so we would just clean this up this way. This is the best we can do. Okay, that's fine. So product rule works, quotient rule works, chain rule works. All right, so let's look at the next one. The next one is going to be a chain rule. All right, so let's look at the next one. So the thing that the place where we are right now is that we are going to be combining rules, and when we combine rules, we just write it all out, take it piece by piece, but don't jump to the answer. Yes, you get to do that. Yes. Okay, so here's another one.
Would it just be like 3y squared dy over d?
Yes! That's exactly it. I do. I want to do the happy dance. Okay, so let's go back. So yes. So let's write this one side by side.
you're still using the same rules. It's not like
Yes.
change the
No,
change.
this is just, we're just putting everything together. If the variables match, the answer is just 3x squared. Because it's x, this is a basic, x cubed, it's a basic. Y cubed, is that a basic? No, because it's not x. So it's something cubed. There's my something, plain old chain rule. So something cubed says take care of the outside function first. What goes in? And then the derivative of the inside. What's the derivative of y with respect to x? dy dx. Yes. So excited.
But on the other side of the equals, it would still be d over dx.
No, because these are just expressions. Let me jump right to where you need to be, because these are just expressions, they are not equations. So now let's look at an equation.
So do we still keep that y in that case?
This one right here?
Yes.
Yes.
Okay.
Yes, so remember, when you do a chain rule and you handle the outside function, the inside function goes back in. You handle the functions one at a time. Yes.
Does the dy dx always go at the end? It can't be in front?
The order does not matter, but when I'm doing chain rule myself, I'm thinking outside times derivative of the inside. So so when we write the final answer?
Yeah.
So we're all getting to the same
Okay.
place, so I'm going to do that example right now. Okay, so let's look at this. So now we're going to do, let's first do an easy example, and then I'll kind of lay out what the plan is. All right, so here's an easy example. I'm making it up. I know, it's always dangerous, right? All right, so so my instructions are find dy dx. Now clearly, what could you do here?
You could start to solve.
Solve for y and find it, right? That's one option we know we can do. So let's hold off on that and not do that yet. That's a good way to check ourselves. We know we can do it that way. I could d dx the entire thing. Actually, let me make this a 10. Just put a 1 in front of your 0. Okay, so I know you hate to erase, I get that.
Like everybody.
All right, so here's the thing. We're going to d dx. If I want to find dy dx, I know if I took the derivative of y with respect to x, I'd get dy dx. So I'm going to d dx the whole thing. And we're just going to go term by term, taking the derivative. So the derivative of x cubed, is that a basic? Yeah. I know that, so that's just going to be 3x squared. Minus derivative of y with respect to x. What do I need to write down?
dy
dx. Derivative of 4, 0. Derivative of 10, 0. What am I trying to find? dy dx. So now solve
dy
for it.
dx equals 3x squared.
dy dx. Yes, if I put,
Negative.
no, it'd be positive. You write the first time. So if I were to subtract 3x squared from both sides and divide by a negative, or
Oh, yeah,
dy dx on the other side, however you want to get to that. So this is our answer. How do we? What if we were to come back up here? You look puzzled.
Where'd the negative go?
Because if I add dy dx to both sides,
Oh, okay, okay.
okay. If I had solved this for y, I would have gotten y equals x cubed minus 6,
Right.
and the derivative dy
0,
dx,
3x squared.
3x squared, same thing. So this is all very convenient because I could have solved this one for y if I wanted to. It's like the product rules that you could multiply out and do that way. Yes.
So, in theory, if we have a complicated function
Mhm.
where we may not be able to separate the y by itself because we have another function that's unsolved within it,
Right.
we can use these
Yes.
rules
Yes.
to find where
Yes.
before we wouldn't be able to isolate.
Correct. Right. Exactly.
Okay.
Yeah. Okay. So let's do another one.
Can
So
you keep that up?
yeah. Well, and I'm going to come over here and kind of write our list of instructions. So I
Like when you
think
were talking about that y plus ln of y.
yes, we're going to do one like that. All right. So here's the deal. When we start with an equation that's implicitly defined, we're going to find d dx for both sides. So this is implicit defined. I use the word function. This one was pretty easy. There was only one dy dx. Not usually the case, because in a case like this, I just solve for y, right? This is, I wouldn't do this implicit differentiation. I would do it this way.
Right.
So let's look at, we're going to anticipate that it's going to be more complicated. So after we take the derivative of both sides, then we're going to collect, so 1, 2, collect all terms with a dy dx on one side, everything else on the other side. So remember, we're trying to solve for dy dx. That's the whole point. So we're going to get all the dy dx's on one side, everything else on the other side. We're going to factor out the dy dx. Because you're going to have multiple terms now. Remember, we're thinking complicated. We're thinking we're going to have a couple of different terms with dy dx on the one side. So we're going to pull that dy dx that's common, right? We're just factoring out the common part. So we're going to factor out dy dx. And then lastly, we're going to divide by the factor. So then we're going to do a division. You'll see when you do the next example, it's easier. Division to solve. All right, so let's look at this one. So again, the instructions so far are find dy dx. So find the derivative. And so here's what we have. Y cubed plus y squared minus 5y minus x squared equals negative 4.
Or
Okay. So if I want to find dy dx, what do I need to do to the entire thing? I need to do essentially a ddx. Those are my instructions on the entire equation. Because remember, what I do to one side, I have to do to the other. So we're going to do it to everything.
Is there a way that you could do like d over dy or something?
Yes, we could do it dx dy, but not, not commonly, and I don't want to introduce that right now. So yeah, but it's important, the variable that's in the bottom is important, yes, and it can be kind of anything. So in this case, I'm trying to find dy dx. That's kind of our standard, we're going to stick with our standard form for now. So, d dx of y cubed, is that a basic? No, because it's not x cubed, it's y cubed. So this is automatically a chain rule, right? I've got something cubed. So the derivative of something cubed is that, 3 times the something squared. What is the something?
Y.
Y. Now I need to do the derivative of the inside,
Which is just dy.
dy dx. Right? All right, so that's the first term. Second term, y squared. Is that a basic?
No.
No, because it's not x squared, it's y squared. So something squared, not x squared, something squared. So that's the derivative of something squared times the derivative of the inside, which would just be dy dx. Minus 5y, is that a basic? No, because it's not a minus 5x, it's a minus 5y. So minus 5,
dy dx.
yes, derivative of y with respect to x, dy dx. I can just go straight there because it's just derivative of y. All right, so what about this one? X squared, is that a basic?
Yes.
Yes,
2x.
so minus 2x. Derivative of negative 4? 0. Okay, so now what do we need to do? Remember, the whole point is that we're trying to find dy dx. So the first thing I'm going to suggest is this. Let's clean it up, right? We don't normally write it this way. We normally write 3y squared. That's a lot. So this first step I would write this way, and then I would immediately write a cleaner, tighter step that will make it easier to find things. One of the things I'm going to suggest is that y prime is a lot shorter to write than dy dx. So if you want to replace all those dy dx's with a y prime, it's less for your brain to look at and contemplate. So that will be my recommendation. So as I'm rewriting this, I'm going to write 3y squared y prime. Much simpler. Minus 2y y prime. Minus 5 y prime minus 2x.
Why do you do minus 2y?
Oh, it should be a plus, thank you. Yes, thank you. Okay, so what am I trying to find? Y prime. So I need to get everything that's y prime on one side, everything else on the other side. So stays, 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 other side. All right, so 3y squared, y prime, 2y, y prime, oops, minus 5, y prime, equals 2x. So all I did is put everything that doesn't have a y prime, or if you like to keep it dy dx's, please feel free. Next class, I'm not going to make this substitution because when we do related rates, it's really much better to keep kind of this original notation. But either one is fine. So now, I've got all of these have y primes in it. So they all have something common. So let's pull the y prime out front. What do I have left from the first term? 3y squared. And the second one?
2y.
And the third one? Minus 5. So now, if I'm trying to solve for y prime, what do I do next?
Well, that whole parentheses.
I take this whole thing, divide both sides. So I'm going to get, very commonly for implicitly defined functions, when you find the derivative, you're going to usually have a quotient for your answer. And it's going to have x's and y's in it. That's okay. It's a little weird, but that's okay. So here I'm going to have my final answer. If you want to go back to dy dx's, you can, you don't have to. 2x divided by this whole thing. 3y squared plus 2y minus 5. So the process is actually pretty straightforward. The important thing to remember is that we keep asking ourselves, is it a basic? Is it a basic? Is it a basic? And a basic is defined by
X.
just a function of a plain old x. And if it's not that, it's a chain rule. So here, this is easy because the inside, the derivative is always just dy dx. So that makes it pretty easy. Okay, so now I want to introduce one more kind of notation, and that is this. If I say if I write this, what that means is this line is like an evaluation line. We're going to use that later in the semester as well. And what this is saying is plug this point, AB, into here. So this is just my shorthand way of saying substitute. With one variable, if I have f prime of 2, I can say substitute 2 into f prime. That's easy. I don't have a good way to write that this way. So the way I write it is dy dx, line, meaning evaluate at that point. And you can see why I might need both points, because here I have both x's and y's, right? So it's got to be a point that's on the graph, so will that work? Yes. All right, so I think the point 1, 1 is on this graph. Is that true? 1 plus 1 minus 5 minus 2 minus 6 equals -4. Yes, so the point 1, 1 is on this curve. So if I could take this and I could say evaluate it at 1, 1. And that means just put the 1 in for x, 1 in for y. Okay, so that's all that means. So this would be 2 over, that's all right. We'll talk about that. So what do I get? This is good. This is good. Optional review. Remember, I've now added optional review problems to the problem set. You do not have to do them at all, but if you want to kind of keep some of your old skills a little bit more current, they're just 2 or 3 problems to do. So this is a good one. 2 over 0. What is that?
Isn't that like a...
Covered.
It's undefined, right? This is going off to, this is undefined. So at this particular point, 1, 1, which is on this graph, it's a vertical slope or a vertical asymptote. I don't know the graph well enough to know. So this one's undefined. Okay. All right, so now let's look at a couple of examples. So I'm going to have you do this one. Yes? And then yes.
Do we know, I'm not sure if we know this or not yet, but, so what do you do when you have x and y within the function of another function? Do you separate them, or do you just not know the algorithm to solve that?
No,
Like,
so...
you have like 10 to the 2y plus x, and you're trying to find the derivative of it.
Yes, you could do that. It's
Do
just,
it separately, or?
well, you would, so here, let me just write down the example you just gave. We won't do that one, but we'll just talk about it. All right, so you said 10 to the
2y plus x.
x. So if I wanted to find, if this is, and this is equal to 3, whatever it's equal to. So if I wanted to find this, is this a basic? No, so if we were to ddx this whole thing, not a basic. 10 to the something, I know what that is, right? That derivative is 10 to the something, ln 10, times the derivative of the something. Can I find the derivative of that?
Oh, okay.
Just
Yeah,
in pieces.
I get that now. All right,
Yeah.
Roger.
Yeah, so this one would get, we'd have to be careful. All of the problems we're doing for product rule, quotient rule, chain rule, and implicit differentiation have a lot of algebraic manipulation. So you just gotta, it's not hard per se, it's just maybe several lines. So you just need to, build up some stamina for working through the problem. And so this is one that would just have some algebra to solve.
Right, okay,
Yeah.
I get it now.
Okay, all right, so let's do
So it would just come out to 2 dy over to x
plus 1, and then you would
and
just
you
have to.
solved it out.
Exactly.
Okay, I get it now.
All right, so here's one. Find the slope of the tangent line to the graph x squared minus y equals 4 e to the y at the point 2, 0. Are we still going?
Yeah.